So epoxide opening under acidic conditions. So epoxides are ethers that are very reactive in contrast to ethers that are not epoxides. So epoxides have a lot of ring strain. They're these little 3-membered ring cyclic ethers. And so much more reactive than other ethers, and they can open up either under acidic conditions or under basic conditions. So we're going to take a look at the acidic conditions. So I'm going to draw an epoxide, and I'm going to specifically pick one that is not symmetrical. So I'm going to go ahead and throw an alkyl group here so that we have one carbon atom that is more substituted than the other carbon atom. And so let's say we react this with an acid catalyst and a weak nucleophile like methanol. And so what we're going to see here is the first thing that's going to happen is your ether, that oxygen, can act as a base, and it can react with the proton source. So this might be something like a little bit of sulfuric acid or some other strong acid catalyst. So we'll have that react. And so we are protonating that oxygen, which is going to make this ether even more reactive and make it into a good leaving group. And so when we open this up, we need to consider where the nucleophile is going to attack. So under acidic conditions, this is the key difference between acidic and basic conditions, the nucleophile will attack the more substituted carbon center. So it will attack the more substituted carbon of this epoxide. So that means that I'm going to show the methanol attacking this carbon here rather than the bottom carbon in this example. So I have the methanol, and we're going to pay attention to the stereochemistry because this attack is all in one step. So it's pretty much an SN2 type attack. So that means that this methanol is going to approach from behind the plane of where the leaving group is. And we're going to break this bond. So what happens in this step, if we draw the product, is that this methanol came from behind the plane, right? Because our leaving group was on a wedge. So this new bond to the oxygen is going to be on a dashed line, which essentially just takes and flips that ethyl group forward. So we'll see the ethyl group now on a wedge. And this oxygen that attacked had a bond to hydrogen and also a bond to the methyl group. So we have kind of this protonated ether, and we broke this bond, but the bottom carbon is still attached to the oxygen, which is attached to the hydrogen, so we have an alcohol there. And notice the stereochemistry. This bond was a wedge, and this carbon center was not involved in this reaction at all, so the bond doesn't change. And so this is almost the product of this reaction. The final thing we need to do is just get rid of that acidic hydrogen, so we have another equivalent of methanol. These would be conditions where methanol would essentially be the solvent, so you would have a lot of it, so you can see it playing more than one role. And so the methanol would come in and take this extra proton. And so the product of this reaction, right, we'd be able to see that the alcohol attacked the more substituted carbon. We'd see the stereochemistry flip at that center because of the SN2 attack. And we'd see that this carbon here still maintains its stereochemistry. So the key things here with acidic conditions is that your nucleophile is attacking the more substituted carbon. And at that more substituted carbon, if you had a chiral center, you will see inversion of chirality. And that is because this attack is an SN2 attack. And so it's going to approach from opposite the leaving group.